Apply the properties of exponents to write an equivalent expression. Here we can think of this a having an invisible exponent of 1. Our property for the product rule says if the bases are multiplied together, we can add the exponents. So this one should have an exponent of 8 for our answer. Complete 1 through 4 independently. This one says, could 10 to the 0 equal 10? Use the product 10 to the 0 power times 10 to the third to show whether it upholds the property. X to the m times x to the n is equal to x to the m plus n. So we have 10 to the 0 times 10 to the third. Using this property, we should be able to add the exponents. 0 plus 3 would give us 10 to the third. If I replace 10 to the 0 with 10, like you see here, then the rest of the problem would say 10 times 10 to the third is equal to 10 to the third. But we know that this would be 1 10 and then 3 additional 10s. So this would indicate that it should be 10 to the fourth. And 10 to the fourth is not equal to 10 to the third power. This means that 10 to the 0 cannot equal 10. Well then, could it be 0? If I replace 10 to the 0 with 0, 0 times anything is 0. But it's supposed to come out to 10 to the third if we use our exponent rules. Those are not equivalent. That says 0 is equal to 10,000. That is not a true statement. So 10 to the 0 power cannot equal 0. Number 3 says, could 10 to the 0 equal 1? This is supposed to come out to 10 to the third. If I replace 10 to the 0 with 1, 1 times anything is itself. So 1 times 10 to the third is 10 to the third. This works. So that means 10 to the 0 power does equal 1. In problems 4 and 5, the expanded form of a number written with exponential notation is given. Write the number in standard form. Well, 4 times 10 to the second would be 4 times 100, or 400. 3 times 10 to the first would be 3 times 10 for 30. 6 times 10 to the 0, well, 10 to the 0 is 1, and 6 times 1 would just be 6. In standard form, this turns into 436. Seven times 10 to the third. 10 to the third is 1,000, so that first piece is 7,000. 10 to the second is 100, so that would be 500. And 10 to the 0 is 1. 1 times 1 is 1. In standard form, 7,501. Now in problems 6 and 7, the standard form is given, and we're going to write it in the expanded form using the exponential notation. So we have 900. 100 is 10 times 10, so we can rewrite that as 10 squared. We have 80, that's 8 times a single 10. And then we have 2. We just want 2 times 1. Well, 10 to the 0 power is 1. This next one, 10,000, would be 10 to the 4th power, and we have a 1 in the 10,000 spot. We don't have to worry about the 0. 7 is in the hundreds place, which is 2 tens multiplied together. The 3 is in the tens place, so we need 1 10. And then the 5 is in the ones place, so we don't need any tens. Apply the property of exponents to write an equivalent expression for x to the 0 times x to the n. Then show that the definition x to the 0 equals 1 upholds the property for any non-zero. So we're going to start with this. X to the 0 times x to the n. Well, 0 plus n is just x to the n. Now we're going to show that if we replace x to the 0 with 1, that this property is still going to work. So in that position, we'll place 1. X to the n times 1, anything times 1 is itself. Since these two things ended up the same, we know that x to the 0 can be replaced with 1. So let's add that to page 81. We're going to add the description of the 0 exponent. By definition, anything to the 0 power is 1. Well, it does say for a non-zero. So, for example, 5 to the 0 power is 1. In problems 9 and 10, and then 11 and 12, we're going to determine the value of n. 11 to the 4th times 11 to the 10th equals 11 to the n. I believe in the student edition it has a different value there. I believe in the student edition it says a 0 here. So following that property, when we have bases multiplied together, we add the exponents. So 4 plus 0 is 4. That is in the n position, so n has to equal 4. In this problem, negative 4, we have 2 plus n, has to equal negative 4 to the second power. So here, if 2 plus n equals 2, n has to equal 0. With the bases multiplied together, we add the exponents. And that's supposed to equal 1,000. Well, 10 to the 3rd is 1,000. So that means n has to be 0 because 0 plus 3 is 3. Five to the 0 times 5 to the 0, we add those. Well, 0 plus 0 is just 0. But let's take it a step further. Anything to the 0 power, 5 to the 0 power, would be 1. So that means n has to equal 1. We're going to go through these rapid fire. They are not in your workbook, but here, anything to the 0 power is 1. This one, we would have a 1 here and a 1 here, so 1 plus 1 is 2. The inside is 1, and 1 to the 3rd power is 1 times 1 times 1, which is just 1. Negative 4 to the 5th is all to the 0 power, so it is equal to 1. This is 1. But then we have 7 to the 5th times 7 to the 3rd, so we add those exponents, and we will get 7 to the 8th. This is 1, this is 1. 2 times 1 is 2, 1 times 3 is 3, and 2 times 3 is 6. To the 0 power is just 1. 1 to the 3rd, 1 times 1 times 1 is 1. This is to the 0 power, so it is 1. This has an invisible exponent. 0 times 1 is 0. 0 times 5 is 0. So this is 1 times 1 for 1 as a final answer. However, this one, 5 times 1 is 5. 5 times 0 is 0. This piece becomes 1. So it is just 6 to the 5th power. All of this is to the 0 power, so it is 1. In this case, 6 is to the 5th power, but 10 is to the 0 power for 6 to the 5th times 1, which is 6 to the 5th. So you could see that we determined how to figure out something to a 0 power by looking at other common misconceptions. Is 10 to the 0 power equal to 0? Is it equal to 10? Or is it equal to 1? And we determined it based on how it upheld the properties that we know so far. So an integer or a fraction to the 0 power is